Hey y'all. Today we're going to introduce a new type of equilibrium, solubility equilibrium. Now, solubility equilibrium, something you have to keep in mind is that we've already talked about solubility in the past, so don't get too nervous about this topic, okay? It is a challenging application of equilibrium, but at the end, back in Unit 2, we've already talked about what it means to be soluble. So let's recap that, remind ourselves what solubility is, and then what we're going to do is we're going to advance into how we're going to look at solubility starting now when we're not assuming things are either fully soluble or fully insoluble. Let's take a look. One thing to note is that there are a few different ways to measure solubility. The most common way that we've used in the past has been molarity, moles per liter. However, there is something called gram solubility, where we can be measuring things in grams per liter or grams per milliliter, or even grams per 100 milliliters. The key to solubility is just figuring out how much stuff can dissolve into a solution to the point where it reaches equilibrium. As with everything in equilibrium, we assume that any of these processes that we consider to be at equilibrium are reversible. What this means is that the dissolving process is going to be reversed by the process of precipitation. Because we're at equilibrium, the rates of dissolving or dissolution would be equal to the rates of precipitation in a solution that is at equilibrium. Earlier in equilibrium, we used Kc and Kp to determine whether a reaction favored a forward direction or the reverse direction, so whether the products or the reactants were favored. In Ksp, we're going to do a lot of the same, but instead of Kc or Kp, we're using a new one, Ksp, or solubility product equilibrium. The larger the Ksp is, the relatively more soluble a salt will be. The smaller the Ksp is, the relatively less soluble a salt will be. In general, we're going to use the tipping point of 1. If the Ksp is greater than 1, we're going to say the salt is soluble. If the Ksp is less than 1, it's not soluble. However, even a Ksp of less than 1 is going to have some level of solubility. There are going to be ions in the solution, and it's going to find equilibrium at that point. Let's generalize how to write a Ksp expression. With a Ksp expression, what we're going to do is we're going to look at the products. In this case are the ions, ion A and ion B. Now, ion A is a cation, ion B is an anion. And in our equilibrium expression, what we're going to do is we're going to plug their values in for our products, right? Remember, it's products over reactants, though. Now, this is where things get kind of tricky. In solubility equilibrium, our only reactant is a solid. And I've told you that solids don't show up in equilibrium expressions because they have constant concentrations. This is the case here too. When we were to take the equilibrium expression and place a solid in it, we turn that solid into a 1. So really what it would be the concentration of A ion times the concentration of B ion over 1. So the way we're just going to write it is it's going to be Ksp is equal to the concentration of A raised to the power of its coefficient times the concentration of B raised to its coefficient. The coefficients, when they dissociate, remember, are equal to the subscripts that existed in the ionic compound itself. So big A had a subscript of little a, so in the equilibrium expression, it's going to have an exponent of little a. Big B had a subscript of little b, so in the equilibrium expression, it's going to have a coefficient or an exponent of little b. Let's do an example where we can put some numbers to this and try to formalize it in your mind. All right, so let's do a practice problem where we're going to write the equilibrium expression for this copper 2 sulfide. Copper 2 sulfide, when it dissociates, all right, is going to dissociate into its ions. Write the ionic equation for this dissociation process and then turn it into an equilibrium expression. How do we do this? Well, first we need to look at the copper sulfide itself. It's copper 2 sulfide, and I know that because sulfur has a -2 charge. Therefore, because it's a 1-to-1 ionic ratio here, we're going to see that copper has a +2 charge. When they dissociate, it dissociates into Cu2 plus and S2 minus. They're in a 1-to-1 ratio. Each one has a coefficient of 1. This means in our equilibrium expression, the Ksp is going to equal the concentration of remember brackets because concentration is always shown in brackets, concentration of copper 2 plus to the first power times the concentration of S2 minus, again in brackets, raised to the first power as well. So that's going to be our equilibrium expression. All right, so how about you do one now? We're going to look at the dissociation of gold 3 chloride. I want you to right now write the ionic equation for the dissociation of gold 3 chloride, and then write the equilibrium expression. Once you've done it, come on back and we'll explain it. First thing to keep in mind here is that chlorine has a -1 charge, gold has a +3 charge in this situation because it's gold 3 chloride. What this means is that it's going to dissociate into 1 gold ion with a 3+ charge and 3 chloride ions with a -1 charge. So that's going to be our ionic equation here. We're then going to plug it into our equilibrium expression. Gold with a +3 charge in brackets times chloride with a -1 charge in brackets with the chloride ion cubed, raised to the third power. That's going to equal our KSP. Now in the next part of this video, we're going to look at saturated solutions. A saturated solution is a solution that is at equilibrium. Now, in order to be at equilibrium, this means that the processes of dissolving and precipitation are equal. The rates in both directions of our reaction equation are the same. So we're not forming more precipitate, we're not dissociating more precipitate, we are simply staying constant in terms of our concentration of the solution and mass of precipitate that exists. One of the pieces of evidence that we use to determine if a solution is saturated is by looking at the bottom of the solution. If the solution has solid precipitate at the bottom, we know that the solution is going to be saturated as long as we've given it enough time and stirred it to make sure that it fully dissociated. One thing to note, that if we already have a saturated solution and we add more of the solid to it, none of that solid is going to dissolve. All right. So again, a saturated solution, the evidence of a saturated solution is that solid at the bottom of the actual beaker or flask where we have that solution. One of the most common ways that you're going to see solubility equilibrium in practice and on tests is through particle diagrams. We've already done a lot of particle diagrams this year, but for solubility, it's really important to keep a couple of things in mind. The first thing is that we need to make sure that we have representations of things that are in solution versus solids, and that you make it clear whether something is in the solution or a solid on the bottom, okay? And you do want to make sure that relative size is shown as best as you possibly can. Make sure all particles in your particle diagrams are labeled as well. If it's an ion, make sure it has a charge. If it's an atom, solid at the bottom, make sure it doesn't. Let's represent a chemical reaction using a particle diagram. Here I've got silver nitrate reacting with sodium chloride. It's going to be a double replacement reaction, which means the silver is going to end up with the chlorine and the sodium is going to end up with the nitrate. Sodium nitrate is fully soluble. Silver chloride is not. So what's going to happen is as long as it's reached saturation, the silver chloride is going to precipitate out. So let's take a look at what this would look like in a particle diagram. First thing to keep in mind is that our original two solutions, everything is going to be in its ionic form. The silver and the nitrate are both in their ionic forms. The sodium and the chloride are both in their ionic forms. However, when we combine them, the silver and chloride are going to come together to form a solid. When they do that, their charges are not going to be there. The sodium and the nitrate, because of the fact that they are spectators in this process, they're going to remain in the same form, same number, same ratio, same everything as they were in the original beakers. Remember, in particle diagrams, we're also going to be able to represent things like excess ions. All right, so if we have a limiting reactant, we're going to be able to show particle diagrams of a limiting reactant. All right, so again, we're not going to focus on that in this video, but just keep in mind that particle diagrams are a really functional way to show a lot of different things all at once. Stoichiometric ratios, concentrations, precipitates, all of that can be represented in particle diagrams. One last thing to be aware of in solubility equilibrium is that we're going to have a new measurement, a new variable, and that's going to be called molar solubility. We represent that with a lowercase s. Molar solubility tells us how much stuff can be dissolved into a solution to the point where it reaches equilibrium. And the units of molar solubility are in moles per liter. In other words, how many moles of the thing, the ionic compound, can be dissolved into a solution until that solution is saturated or at equilibrium. We're going to talk more about molar solubility in upcoming videos, both in terms of what it means, but also how to use it, how to find it. And that's going to be a big part of this unit as a whole. So that wraps up today's video. Today we looked at solubility equilibrium. We started by discussing what is solubility equilibrium. We started talking about KSP and how to write equilibrium expressions for solubility product equilibria. And then we talked about particle diagrams and how we can use particle diagrams to represent solutions and solutions at equilibrium. Going forward, we're going to be looking a lot at how to do this mathematically and also building a little bit more into the conceptual nature of solubility equilibrium. Today's video was written, directed, and produced by Sophia Xu and Ellie Wu. Thank you all for watching. Hope you enjoyed it, and I'll see you in the next one.